All right. All right, let's see. We've got how many people here? No, wait another minute or two. I have to apologize. I forgot to record the alumni panel on Friday. But we will have a few alumni visiting this class over the next few weeks, one in March and two in April. So there will be a chance to hear in this class from some alumni working in optics. But one of them was talking about her work at a company that does adaptive optics, and they're actually paying for her to get her master's online from University of Arizona. We've had a number of students who have gotten their master's from University of Arizona, and more than a few of them have gotten their employers to pay for it. So that's something to think about. University of Arizona is the top optics program in the country, and we've had a lot of luck placing students there, especially the ones who are working in the field, because it demonstrates some ongoing practical knowledge of the subject, and they like that. Let's see how many people. Oh, 1 or 2 more minutes. So a little note of history, something that often gets debated. It's controversial and doesn't matter which side of this we're on, but just as a note of history, standardized tests are controversial, and one often sees many opinion pieces these days on standardized tests. And oftentimes people making some point for or against them will say, ever since standardized testing began in the late 19th century, what's the problem with a sentence like that? Regardless of what they say next, for or against it, what's the problem with a sentence like that? Any guesses?
Was there standardized?
What?
I was going to say, was there standardized testing before that?
Standardized testing began about 2,000 years ago in China. And so whenever I hear someone make some point for or against it by pointing out, well, you know, in the past 100 years, here's what's happened with standardized tests. I'm like, we've got 2,000 years of experience with them. And I'm not going to say Imperial China was the greatest thing that the world has ever seen. It wasn't the worst. It was a society with its problems, its achievements, its ups and its downs, and you can say whatever you want to say for or against it. But whenever I hear someone make their historical argument by saying standardized tests were invented in the United States in the late 19th century, I'm like, you know, there are other continents, there are other societies. Some of them are quite old. You know, in America, if you point to a building, you say, yeah, this is really old. This was put here 200 years ago. In Egypt or Iraq, if you say, yeah, it's a 200-year-old building, so be like, oh, it's new. Wow. Yeah, you've some recent additions to the city. But we tend to think that the world began in 1776. It's a rather strange thing. Okay, at this point, I'm going to get started with applied optics. We've been waiting a few minutes. Um, for the first part of today's project, did any of you find that you got exactly identical graphs?
Yes.
Yeah, but Spencer, was that you? Or was that Felipe?
No, that was me.
Well, Spencer, you shouldn't have gotten identical graphs after what we did in office hours.
Well, yeah, after what we did, I didn't, but before I did.
Okay. I'm postponing the project since there was someone besides Spencer who had, I'm postponing the project till Thursday. And the reason is that it's something to do with the ZMAX feature that I went over a little bit, but it's a new feature that we're using for the first time. When you try to optimize something, and here I should probably, I don't want to mess up anything that I have in this file. So I'm going to go to one of my older files. What was it? It was merit function test there. So imagine that I change an assignment. I make an edit to an assignment, but I don't tell any of you. Are you going to do the assignment differently? No, of course not. So let's say that we change our fields. We have object height. I don't know. I change from an object height of, well, let's just first do this for something that's actually on axis. We'll just put everything on axis initially. Okay. And then we go to optimize and we go into our optimization wizard and we check, we'll do spot size, but it's not going to matter much. Spot size, apply, close, merit function editor. And then we tell it to optimize this lens. So it does it. Great. The merit function, when we did that, the thing that sets up the merit function, the thing to be optimized, checked all of our settings and said, okay, I'm going to use that. And then I go and I change this setting. Let's make it 10 degrees like it was in the assignment. So I go and I change this setting and I tell it to optimize again. Well, nothing changes here because these are the settings. These are the radii that optimize the lens for the merit function settings that we were using before. We didn't update the merit function. We didn't tell it anything new. So it doesn't change anything. Just like if I were to change the assignment, but not tell any of you guys, you just do whatever version of the assignment I already posted. So when you change things on the left, but you don't go back into the optimization wizard and tell it to update the merit function with the current settings, which you do by clicking apply, it just continues to use the old settings, uses the old field positions. But now that I've gone in there and done that, let's see if it changes. Yep, it did change a little bit when we had the off-axis field. So because that is a software issue, I'm going to postpone the thing until Thursday. But of course, that won't mean anything unless I click update. So I am going to put that on Blackboard right now for See, until I pass that information along, it's not useful to everyone. Likewise with what we did in ZMAX. Any questions on that?
If I turned mine in like 5 minutes before 5, like that first submission won't matter, right? If I submit it again before Thursday.
You should have more submissions open, but what I will also do right now is I will go in and edit the settings on that assignment. Minimizing spherical aberration. Edit. We will first change the due date to Thursday. And I gave everybody 3 submissions. Now you have 4. So even if you used up all of yours, you've got 1 more chance. Anything else? So yes, you can resubmit. And I'm only going to grade the last submission. Anything else? Okay.
Professor,
Yeah, go ahead, Ken.
So when we're optimizing our biconvex lens and after we click on the optimization wizard and the optimize button, would we also click on the quick focus button as well to just to like, you know, finalize everything?
Well, what quick focus does, well, that's a good question. Let's check. I predict that quick focus might change something, but if it does, it'll only change it probably in the last decimal place. Quick focus only ever changes the last layer thickness. And occasionally people have said that they did, and there, it changed it in the last decimal place. And the question is, why, if we already optimized it with a quick focus, or sometimes you might do a quick adjust. We could do a quick adjust on this one right now. And it changed it in the last decimal place. People ask, if it was already optimized, why is that? And the answer is that the answer is that I have to switch to drawing in order to really explain this. All right, so we are trying to either minimize a spot size or maybe maximize something that's a good thing, but whatever. Either minimize the undesirable trait or maximize a desirable trait. It doesn't really matter either way. The same basic principle applies. So it's going to be some complicated function of our parameters, okay? This is some lens parameter. And here is our image quality. And in fact, this is actually, we have in this case with this lens, 2 variables that it can play with. So I should really draw a third axis. Why is that not working? Okay, anyway, I should really draw a third axis and indicate that this function is coming out of the page, except they're no good at 3-dimensional perspective drawing. But in any case, it's trying to, we'll get rid of that. It's trying to find the minimum. Now, we as human beings see the entire curve drawn continuously. And we say, well, the minimum is right there. Except the computer doesn't have that entire curve. In order to have a continuous curve, the computer would have to evaluate that function at an infinite number of points, which means it would have to try an infinite number of lens configurations. And then for each of those infinite number of lens configurations, calculate a spot size. And if the computer were to do an infinite number of cases, not only would you miss today's deadline, you would miss Thursday's deadline as well. So a computer doesn't do that. What a computer does is it tries to find the minimum by trial and error. So it starts off, I don't know, maybe here. And then it tries here and there to see which of those steps. I'm giving you a very oversimplified version of the idea right now. People get their PhDs in applied mathematics trying to come up with Yes, it's called gradient descent, and subtle variations on gradient descent and many other ideas like that can occupy someone for their entire PhD studies in applied mathematics. But basically they would see, well, okay, which direction improves things? And they see that this direction improves things. So maybe they take another step and another step. And then they find that, hey, that step probably didn't make anything better or worse. So they're going to backtrack and they're going to try a few steps in this area. And they're never going to get it exactly because they don't know, they don't have an infinite number of points. They're just going to keep going and they're going to take smaller and smaller steps until the subsequent improvements are too small to matter. And then they're going to say, okay, we're good. Well, then you could always tell it, hey, try a few more steps anyway. Clicking on quick focus after it's already worked on that, or clicking on quick adjust after it's already worked on that, basically tells it, I know you already took a bunch of steps, but try a few more. And when you try a few more, it will ever so slightly improve things in the last decimal place. That's the idea. Any questions? Trying to improve functions of many variables that have very complicated input parameters, like I said before, could be the subject of a PhD dissertation. It's why people work on things like machine learning to try to see if they can infer from patterns what might be the best way to do it. It's part of why people work on quantum computers, because there is a database search algorithm. And you could say, well, what does there's a database search algorithm that works much faster on a quantum computer. You could say, what does searching a database have to do with that? Well, it's about checking a list of possibilities. And so in general, this is a very hard problem. And every time we add another variable, you know, it multiplies the number of cases that we have to try, which is why if we wanted it to optimize a lens with 30 surfaces, you know, we might be here for a while. And if we wanted to optimize a lens with 60 surfaces, you know, maybe before the sun goes supernova, it would solve the problem. All right. Let me show you another thing in ZMax. So I'm going to go to a file called Basic Thin Lens, which I posted on Blackboard today. And I made this one as simple as humanly possible, meaning that the material is N15, which stands for refractive index 1.5, just so that all of our calculations would be as simple as humanly possible. Now, if I make this, well, let me undo that. Don't worry about what that was at the moment. Naively, we might think that, okay, if I've got a radius of curvature of 10 and minus 10 and a refractive index of 1.5, well, then let's just see here. 1 over f equals 1.5 minus 1 over 10 plus 1.5 minus 1 over negative 10 equals 0.5 over 10 plus 0.5 over 10 equals 1 over 10, f equals 10. And if f equals 10, then if we place the object 2f away, the image should form 2f away. And I will turn off my annotate. We go into the layout and yeah, this looks pretty good, except that if I zoom in on it, it's actually not perfectly focused. And you could say, well, you know, that's spherical aberration, because spherical aberration makes rays focus closer in. Duly noted. Still not, okay. hard to tell at this point, but very hard to tell, but it's definitely a little bit thicker on the right than over here. Now, if I were to just do a quick focus, we're not going to see anything on there, but let's have it do a quick focus. I fix those to be the same. Huh, didn't quite focus there. I'm going to make it thinner, do a quick focus again. Well, now it didn't change at all. So it seems like this lens is not quite obeying the thin lens equation. Any ideas why it's not obeying the thin lens equation? Just look at it. Tell me why the shape in front of you is not obeying the thin lens equation.
Not thin.
It's not thin. That's the entire problem. It is not a thin lens. And some of you may have noticed down here that in most of your assignments, Zemax has been quoting an effective focal length, which is never quite what you thought it would be. All right. It's never quite 10 in this case, or whatever you designed your lens for. Now it gets even more interesting. I could always make this one be 20. And then I could force this one to be biconvex, because we know that not just biconvex, but symmetric biconvex. So we'll pick up from surface 1. Actually, we're going to do a different thing right now. We can force this lens to have a focal length of 10. It's called a power solve. What Zemax does is if you tell it to fix the element power, it takes this surface and the one before it and treats them as one lens. And then you tell it what the power of the lens is. But for a variety of reasons, the power of the lens is 1 over the focal length. So if I want a focal length of 10, the power is 1 over 10, or 0.1. And it will do that, right? It will make it have a focal length of 10. And now at the bottom of the thing, it says effective focal length 10. And we can actually make this, we can force this to be symmetric through a process of trial and error. I'm going to make this, I make this surface 9.9. So I make the left surface a little more curved. Remember, smaller radius of curvature means slightly more curved. The right surface becomes a little less curved. I'm going to try to get these to match up with each other. 9.85, well, now it's negative 9.868. So I'm going to make it 9.86. And now it's 9.858. So then I'm going to make it 9.859. And the thing that optimizes it is the same, at least to 3 decimal places. And there's got to be some setting in here I could use to reveal more decimal places. But I'll tell you honestly, this is not just me being lazy. If your engineering design requires that many decimal places, there are times when that matters. There are times when that's necessary, but you really don't want an elaborate machine to have more than a tiny number of parts with those kinds of tolerances. And now it still says effective focal length of 10. And these are 20 apart. We have forced this thing to have its principal planes on the left and right surfaces. Okay, we have forced it to have them there. But if I were to just simply say now that, well, let's just leave that alone. What we want to understand is thick lenses. And we are going to need the tools of matrix optics in order to derive what we could call the thick lens equation. Any questions? Okay, I'm going to switch to drawing. So to review what we were doing last time, we have a ray. We can characterize that ray by its height, y, and its angle, theta. And we put them into a column vector, theta, y. And then there are things we can do with that ray. If we want to send that ray propagated a distance to the right, we have a translation matrix. Translation is a function of that distance s. Translation of s equals 1, 0, s1. And so t of s on theta y equals 1, 0, s1 theta y equals theta, and then s theta plus y. So translation just moves the ray further away from the axis because it was already traveling at some angle. And then we found that if we had a lens, now I put a lens over here, the effect of the lens is written this way: 1 minus 1 over f 0, 1. All right, and we talked about how this means that theta 2, y2, the new theta and the new y after it passes through the lens, are equal to 1 minus 1 over f 0, 1, acting on theta 1, y1. And that's equal to theta 1 minus y1 over f and y1. In other words, y2 equals y1 because sending something through a lens does not change, sending something through a thin lens does not change the height of the ray. But the new angle depends both on the old angle and the old y, because, well, if I send a ray in parallel to the optic axis here, it goes down at a very steep angle. Whereas if I send it in parallel to the optic axis here, it goes down at a sharp angle. Any questions so far? Okay, so I've been saying that we can write out things in terms of matrices, and we're going to eventually write out things other than thin lenses. Like we're going to write out things like thick lenses and systems of lenses and lenses with air on one side and water on the other side. But before we can do any of that, we have to test it, not just for the sake of intellectual rigor and consistency to make sure that it gives us the results that we already know, like the thin lens equation, but because everything you will ever do in matrix optics with imaging comes down to trying to figure out which element of the matrix should be zero, right? It's all about finding zeros, because if I've got a lens and I've got some object point, and then I send a bunch of rays through the lens to an image point, well, you tell me, does y2 depend on theta 1? all of these rays here on the left have different angles. This one made a shallow angle below the axis. This one made a really steep angle below the axis. Does the y2 here depend on theta 1?
No, it doesn't.
No, they all got to the same y. Now, what if I was over here? And I extrapolate those rays to this plane. Does y2 depend on theta 1 here?
Yeah.
Yeah, definitely here. What about over here? Does y2 depend on theta 1?
Yeah, again, it does.
Yeah, because all of these rays, they start off at the same y1. Right, they all start at the same y1. And then they go off with different theta 1 values. They get propagated. They pass through this, they get propagated, they pass through the lens. This is the one special place. This is the one special distance from the lens where y2 is independent of theta 1. Everywhere else, y2 is independent of theta 1. So in cases like this, you're going to have to figure out that one of the elements of the matrix one of these matrix elements had better be 0. Okay, that's the only way that any of this works. Conversely, if I sent in a bunch of rays parallel to the optic axis, and let's say that I've got a really elaborate system of many lenses here for whatever reason. Okay, so then I send in a bunch of rays that are parallel to the optic axis, and they do all kinds of messy things that I'm not going to try to predict. But in the end, all of those rays show up here. Do all of these rays have the same y1 value? Do they all have the same y value on the left side of the lens? If I were to just look, like say here, 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 do these 3 rays at this surface have the same y value?
No, they all have a different one.
But do they have the same theta value?
Yeah.
Okay, well, that's interesting. And if we propagate out to here, I'll call it SF for S final. In this particular plane, does y2 depend on theta 1? Probably, because if I did this, then in all likelihood, these rays would have come out over there. That's how we figure out the focal length of a lens system. You send in a bunch of parallel rays and you see how y2 depends on theta 1. So it definitely depends on theta 1, but does it depend on y1 in that plane?
No, it doesn't depend on y1.
Absolutely not. So in the top case, theta 2 is a theta 1 plus b y1. Y2 is c theta 1 plus d y1. And I'm telling you that one of these four coefficients had better be 0 so that y2 only depends on one variable that it's supposed to depend on, but not on the other variable. Down here, again, y2 equals c theta 1 plus d y1. Now, I've given you a bunch of hints already. What I want you to do at this point is, before I walk you through any more of that, I want you to go into Blackboard. And I want you to look at the files for today's class. And for some reason, well, the good news is that Zoom works for me. The bad news is that my web browser and email only work sporadically. It seems like they are having a harder time finding my internet access than Zoom is. But I want you to go into the files for today, and you will find a PDF of an activity. And I'm going to divide you up into breakout rooms. I want you to chit chat through that and see if you can work through that activity and figure out the answers to the questions. Don't go into the rooms yet, even though I just clicked open. I'm gonna, since I can't pull it up in Blackboard, I'll pull it up on my screen. And it should be up on my other screen. Okay, so now it's on the screen that I'm sharing, except I clicked waves activity instead of matrix activity. Okay, so if we wanted to describe an array that starts off on the left and goes all the way to the right, then there are two ways we could do it. We would have to first propagate it through a distance S1, then send it through a lens, and then propagate it through a distance S2. And we could do all of that messy matrix multiplication, but we could also just reason it out. And so I want you to go through the 9 questions on here and go into your breakout rooms, and I'm going to spend some time playing with my internet access. I'll check in on you in a few minutes. Andrew, you're gonna join your group. Andrew, you're gonna go into the breakout room?
Yeah, sorry, I just quickly got water.
That's okay.
same y point,
Mhm.
and then they all meet at the same y2. So they all have the same height,
Oh,
but different angles, but they all
Yeah.
meet still at the same height. So
Mm.
theta doesn't change how
Mhm.
y2 changes.
Right.
oh, okay. Wait, let me see if screen sharing is on. We could draw it out.
Oh
on
yeah, with the whiteboard.
Yeah, I just learned how to use this. Okay. Wait, what was the okay? So how was the setup again? So it was
So yeah, draw the lines and then the
Yeah.
axis.
yeah, like this, right? And then the lights, the rays.
Can we download it onto my computer, bro? Oh God.
I
I'm just
apologize.
I'm just kidding.
Yeah, Dr. Small, I'm having trouble signing into my CPP right now for some reason. It was fine an hour ago, but Juan is going to email it to me.
Okay. Yeah, if you need anything that Juan doesn't have, just let me know and I'll email it to you. I have my email working again for now.
Sure.
I used to think it was terrible to have to rely on printers to work when I need them. And then I realized, oh, great, now I have to rely on my ISP to work whenever I need it. And I think I'd rather rely on printers again.
Yeah, I agree. I don't know, because I've been having like internet issues too recently that I haven't been having before. And so I don't know if it's like the whole COVID thing, everyone's at home and everyone's using internet, or if they're like trying to scam me out of out of paying for better internet.
I feel like after a year of this, the network infrastructure would be better than it was before. I think that, look, there's always somebody having network issues. And right now you're one of them and I'm one of them. And by coincidence, we're both interacting when the internet works. I mean, I don't think it's a system-wide thing. It could be that they're trying to scam you and, jack up your price, but I don't think it's a general West Coast thing or whatever, because I think the infrastructure should be better by now. But any questions on this activity?
So far, no. Well, not me personally. I don't know about everybody else.
Anyone else? All right, I'm gonna check on another group.
Thank you.
Any questions in here?
Not yet. It seems pretty straightforward for the most part.
Good. Anyone else?
Nope.
All right.
Before. All right, I guess I can just ask.
Any questions for me?
Yeah, I guess we're kind of all just a little confused whether, like, kind of the initial case that we're dealing with, like you were examining two cases in class where you had like an initial like object and then you had like parallel rays coming in. So I was kind of confused on which one we were doing.
Well, let's assume an object at a finite distance S1, because we've got three matrices on there.
Yeah.
And one of those matrices has a finite distance S1.
Okay. All right, then I think we're good then.
Okay.
We were kind of just doing it for both. So yeah, based on that, we would say theta 1 .
I guess I'm stuck on the last one. I know 8 is like tangent theta 1 equals y2 over s1, but for number 9, I'm trying not to write it out in matrix form.
So let's see, which matrix
One, two.
element, I'll have to check my solutions because I don't remember which one the last one is referring to.
Sorry. Based on your previous answer, the fact that the ray through the center doesn't change direction and possibly within the lens equation, figure out the last matrix element. I think I figured it out. It's theta1 is equal to theta2 since it's going through the center of the lens. And so before we had theta, tangent of theta equals y1 divided by s1. But we can use a small angle approximation to get theta1 just equals y1 divided by s1. But then theta1 equals theta2. And so now we have a relationship between theta2 and y1. And so now we can figure out the matrix element A.
Yeah, that one is the that is the messy one.
Yeah.
And yeah, that's the one messy one that might take some time.
Okay.
Anything else?
Nope, not for me.
All right, I'm gonna give you guys a few more minutes.
using trig, but we'll see. Like, so we said that it'll be at a distance f right here, and then we could just use trig to find that, right?
Yeah.
So it'd be like, oh wait, it would depend on a different theta, I'm guessing. Oh, how do I undo this? Oh no. Tan theta 2 is equal to opposite, right? Kind of like that, because it doesn't depend on the other angles, I'm guessing.
It needs a minus sign.
Oh,
Oh,
a
gotcha.
minus sign.
Yeah,
Oh wait, like right here.
yeah. Tan theta
Oh,
2 is minus y over f. But other
oh.
than that, it's right.
Okay, cool.
Mm-hmm. Professor, we were wondering about the ray tracing for number 6. I know I'm kind of bad at drawing, but is it supposed to look something somewhat like this?
Yeah, that's exactly what it looks like if theta 1 is 0.
Mhm. But I mean, like like at this point, so even this right here is
Yeah.
somewhat
Looks-
accurate.
I don't see anything wrong with that. What is your problem at the focal point?
Like there should be no height to it.
Oh well, but the y is y1.
Oh, okay.
And
Oh,
theta 2 is
that's
minus y1 over f.
oh, that makes sense because of the height of like right here,
Yeah.
kind of. Okay, yeah, there you
Yeah.
go. Oh, okay, that makes more sense. And then we could solve for theta 2 with that.
The last matrix element is going to be tricky. So if you don't quite finish, I'm going to give you a couple more minutes. If you don't quite finish the last one, don't worry. We'll do that one together.
Okay.
But do what you can with it.
Okay, thank you.
How far along are you?
Talking about problem 3 and 4.
So I understand why you say it's positive, but when you say it would just be m, do you mean it would just be 1 over d? The
No.
variable d?
And magnification.
The magnification is S2 over S1. And in this case, it would be negative because if the object is above the axis, the image is below the axis when you just have one lens.
When that happens, isn't m defined to be negative?
Yeah, so M should be minus S2 over S1.
So m should be the d should be positive m because that's how it follows. Oh no, you were right. A negative m. Yeah, got it. Okay.
D is minus S2 over S1. All right, I'm going to check in on another group. What are you working on right now?
Currently, I'm on number 4.
Anything I can help you with there?
Not that I can. I mean, I really like working with matrices, so
You like working with matrices, you said?
I do. Yeah.
Good. It'll help you a lot in quantum next year.
Oh, thank goodness.
Anyone else have a question for me? All right, I'm gonna give you just a couple more minutes and then I'm gonna close the breakout rooms.
All right. Thank you.
Dr. Small, you're muted.
Okay, I'm just checking to see if there's anyone still in the breakout rooms. No, looks like those are all closed. Good. Okay, so I am going to display the solutions. So the first few are pretty straightforward. Does y2 depend on theta 1 if the image is in focus? No, we went over that. And so that means that C is 0 because y2 is C theta 1 plus dy1. And then D should be the magnification minus S2 over S1. Now, it gets a little bit more complicated with theta. Theta 2 is A theta 1 plus BY1. And if theta 1 is 0, then when it goes through the lens, it should make an angle minus Y1 over F. Strictly speaking, it's tan theta 2 is minus Y1 over F, but small angle approximation. Then it gets a little bit messier with the other coefficient, because if it goes through the center of the lens, you might be thinking, well, isn't Y1 0? Y1 is 0 if we were to measure Y1 right at the lens surface, but we're not. We're measuring Y1 off to the side. We're measuring, I'm going to do this part on, I'm going to do this part in writing. So we're measuring Y1 here. All right, so here's Y1. In general, it's non-zero. If it hits the lens at the center, then that means that theta 1 was equal to minus Y1 over S1. Right, so it's a very special case there. And then theta 2 should be equal to theta 1. So you get theta 2 is equal to A theta 1 minus Y1 over F. And that's got to be equal to theta 1. So A theta 1 is equal to Y1 over F plus theta 1. And the problem is we've got this theta 1 that we can't just divide out, because if we did that, we'd be left with A equals Y1 over F theta 1 plus 1. We have to remember that theta 1 is equal to minus Y1 over S1. So A is Y1 over F times minus Y1 over S1 plus 1. Those Y's cancel. And we're left with minus S1 over F plus 1. Any questions on that? Well, that's just working out what these matrices have to be. The other way we could do it is we could actually multiply them out. So I'm going to go into Mathematica, and I posted a Mathematica file today. The way we do matrices in Mathematica is with curly brackets. And by the way, every time, for those of you who have not used Mathematica before, Mathematica, in many programs, you type in a command and you hit enter. Well, with Mathematica, if we hit enter, it just takes us to another line waiting for another command, because it'll let you enter several commands before running them all. In order to run commands in Mathematica, you have to hit Shift Enter. And so the single most common answer to the question, Professor, Mathematica isn't like doing anything. The single most common answer to that question is hit Shift Enter, not just Enter. Now, this is a pretty lousy way to display a matrix. It's a 2x2 matrix, so it's pretty easy to read off. It's still a lousy way to display it. So we're going to use the table form command most of the time, which displays it more nicely. And then I have in here definitions of the translation matrix. Mathematica will not recognize it unless you hit Shift Enter. The matrix for a curved surface, which we'll derive in a little bit. And the matrix for a lens. And so then we're going to do a test. We're going to multiply together the three matrices for a translation through a distance S1, then propagation through a lens, and then translation through a distance S2. Now, why is it that I'm writing these with the translation through S1, the first thing that happens to the ray? Why is it that the first thing that happens to the ray goes last? Any guesses why the first thing that happens to the ray is the last thing we write out? Obviously, none of you know Hebrew, Arabic, or Farsi. Because if you knew Hebrew, Arabic, or Farsi, you'd say, what are you talking about? The first thing that happens to the ray is the first thing that we write out. Because some languages are written right to left instead of left to right. Okay, and I'm sure there are others besides those. Those are just the first ones that came to mind. So if we have the vector over here, well, the first thing that would hit the vector is this matrix. And then the next thing that would hit it is this matrix. And then the last thing that would hit it is this matrix. So as far as what hits the vector and what order goes, we do have the first thing that happens to it hitting it first, and then the next thing that happens to it, and then the last thing that happens to it. And since I often in my classes harp on the idea of math as a language, this is just another example that when you have things operating on a matrix, it's much more like a Middle Eastern language written from right to left. So if we multiply all of those out, then we get this. Now, we had said earlier that these matrices should have somewhat complicated forms, but we said that this lower left element should be 0, that C should be 0. And that doesn't look like 0 to me. But just hear me out. If we write it out, we've got S2 plus S1 minus S1, S2 over F. Well, I could divide everything in there by S1, S2. And I would get 1 over S1 plus 1 over S2 minus 1 over F. Is that 0?
Yeah.
Yeah, that should indeed be 0. If we're in focus. If we don't have the right S1 and S2 values, well, of course, that could be non-zero. But what this means is that the thin lens equation is actually encoded into our matrix formalism. It's just not necessarily obvious on the surface. Any questions? Let's take a break until 6:20. And then at 6:20, we'll talk about the matrix for a curved surface and derive the matrix for a thick lens. So while I was waiting, while I was on break, I was checking out how many languages are written right to left. Apparently, right to left is the dominant thing. Left to right is the dominant thing. Right to left is mostly a Middle Eastern thing. And I had known about this, but I didn't realize just how exclusive it was. Is apparently vertical writing is almost exclusively East Asian, Chinese, Japanese, and sometimes Korean. Although I think that in modern usage, vertical writing is less common.
I think cuneiform was written from left to right. This might be a good reason why.
Yeah, I'm not sure actually. I should check on that. How was cuneiform written? There's apparently there are tens of thousands of cuneiform tablets that have yet to be translated. There are just so few experts who can do it, and more importantly, so little money to pay someone to spend their time doing that instead of doing things like teaching classes on Middle Eastern history. There's more money for them to teach classes on history than to sit there and translate these tablets. So who knows what's in those cuneiform libraries? Okay, let's get back to optics, which is also a Middle Eastern invention, more or less. And let's talk about the lens for a ray at a curved interface. So instead of doing a lens now, we're just going to do an interface. So we've got a ray, it hits.
Dr. Smalley, you're not sharing your screen.
Oh, thank you. Okay, there. So we've got a ray, it hits at a distance y1 from, well, I'll draw it on the other side. Y1, it's making an angle theta1. And then on the other side, it's at a height y2, and it's making an angle theta2. And so we have to figure out theta2, y2 equals A, B, C, D, theta1, y1. Well, let's see. Theta2 is A theta1 plus B y1, and y2 is C theta1 plus D y1. What's y2? Just from looking at the physics of it, what does y2 gotta be? We're only talking about the part where it crosses the interface, not what it does after it's gotten to the other side and then traveled some distance, but just right after crossing the interface.
Essentially y1.
Yep. So what does that mean for these coefficients, for at least two of these coefficients?
C would be 0 and D would be 1.
Yep. Okay, now theta2, we're going to break this into two parts. We're going to use the fact that if we had a ray just hitting here, things would be easy. And likewise, if we just had a ray going parallel to the axis, things would be pretty easy. Things are only difficult when we have both variables non-zero. But if we could just take the case of y1 is 0, then we only have to worry about theta1. And if we could take the case theta1 is 0, you only have to worry about y1. That's the nice thing about linear equations, is you can take one variable at a time. So here's theta1, and here's theta2 if y1 equals 0. And that means that we're just dealing with the coefficient A right now. We're having a hit at the center where the physics is easy, and we don't have to worry about the other variables. So what can we say about theta1 and theta2 at the center? what did the Ibn Saul say centuries before Snell? Snell also said it, but Ibn Saul said it first. What did Snell say?
N1 sine theta 1 is equal to N2 sine theta 2.
Yep. But since we're making a small angle approximation, N1 theta 1 equals N2 theta 2. So, oops, that was not what I intended. What just, okay, there. So that means that theta 2 is N1 over N2 theta 1. So that's telling us that A is N1 over N2. So at this point, we've got 3 of our coefficients. We've got N1 over N2. We've got 0 and 1, and we're about to figure out the last coefficient. And the way I like to deal with the last coefficient is to consider a ray going parallel to the optic axis. And in a case like this, I remember that N1 over S1 plus N2 over S2 equals N2 minus N1 over R. So that immediately enables me to work out theta 2, okay, because S1 is infinity. S1 is infinity, 1 over S1 is 0. So S2 is equal to R over, is equal to N2R over N2 minus N1. Then tan theta 2 must be minus Y1 over S2, or tan theta 2, which is roughly theta 2, equals Y1 times, let's see here, 1 over S2 was just N2 minus N1 over N2R. So that means that our last coefficient is minus N2 minus N1 over N2R. Any questions about that? Let's take a look at the Mathematica file. I'm gonna share my other screen again. And let's go back up. The curved surface matrix, yep, the upper right is N1 over N2. The upper left, well, I had minus N2 minus N1. There, the negative sign is just distributed through, but it's the same thing. N2R in the denominator, 0, 1 in the next row. So let's test this. We could test this for a glass lens with air on both sides. And what we would do is we would just multiply two matrices. The first matrix, the first thing that hits the vector is on the right side. It's going to be a curved surface with radius R1. And N1 is 1 because it starts in air and it goes to glass. But for the second surface with curvature R2, radius of curvature R2, N1 is the refractive index of glass because it goes from glass to air. And the way we multiply matrices in Mathematica is with a dot rather than an asterisk or a cross times sign or whatever. You have to put a dot there. So when we multiply them, we get this. Is this correct? Well, let me phrase this. It is correct. How do you know it's correct? How can you tell? What should the matrix for a lens be? Just look in your notes.
That top right element looks like 1 over F.
Actually, minus 1 over F.
Minus, right?
Yeah, remember that the matrix for a lens, you got 1s on the diagonal, a 0 in the lower left, and then minus 1 over F. And
so factor out the 1 minus n sub g, and then you get the familiar equation.
yeah, because you've got n, no, the focal length, you'd have 1 over F, you'd have an n minus 1, but here we got minus 1 over the focal length. So here it's 1 minus n. And then you've got n minus 1 over minus R2, but we have minus 1 over F. And so the minus sign was canceled with this down here. Any other questions on that? All right, so let's think about a thick lens now, because I introduced this class with a mystery about a thick lens. So we're going to have a lens that has a finite thickness. And I'm going to draw it symmetric just because of the tools available to me, but we're going to have refractive index R1 here and radius of curvature R1 here and R2 there, and a center thickness D. Now, if we have a thin lens, we can measure the focal length simply by seeing how far away from the lens does the image form. But I told you last week that if we have a thick lens or we have a lens system, many lenses, you can't necessarily measure your object or image distances from the surface of the lens, because if it's a thick lens, measuring from here versus here versus here will give you very different answers. Whereas if it were a thin lens, for a thin lens, well, measuring from here versus here versus here or whatever, barely any difference unless you need many digits of precision. So we can't just send in parallel rays of light and see where the image forms, see how far along the axis the image forms. We can't just do this experiment. This is not equal to F. What could we do instead?
What about a beam through its effective focal length?
How would we figure out an effective focal length? What is?
Oh, wait, no, sorry, because it's a thick lens.
Yeah, but how would we measure? Like, forget about formulas for a minute. Just think about what would you do with light and what would you actually measure if you wanted to figure out an effective focal length.
To measure light, I guess the angle
Go on, you're on the right track.
of refraction.
Veering away from the track. Let's try to get back on it. We do send in light at an angle. And by the way, this is the focal point. This is definitely the focal point. And this is, oops, definitely the focal plane. So if I just send in those rays of light parallel to the axis, I do indeed identify the focal point and the focal plane. But I don't identify the focal length because we can't necessarily measure F from this surface here. Okay, this is not necessarily the surface to measure the focal length from. But what can we do if we're sending in light at an angle?
Snell's law.
What's a property of a lens? We found before that if we sent in light at an angle.
Could we use y equals f tan theta?
Yes. So what we do with the matrices is this. We've got our ray. First, we send it across the left interface. So we go air to end glass across something with radius R1. Okay, air to end glass across something with a radius R1. Then we translate a distance D. Because once you've gone across the glass, then so first we go across the interface, refracts by whatever amount. Then we send it this horizontal distance D. So we translate a distance D through the glass. Then we send it across the interface R2. So we're going end glass to air with radius R2. Okay. And that should probably be that if I'm gonna do it right, but whatever. All right, that's what we do. Now, we're not done because if I just multiplied 1, 2, 3 matrices, all I've done is taken an array to this point here. And fine, I figured out that this ray goes to here and this other ray would go to there and this other ray would go to there and this ray would go to there. But have I actually figured out where they meet or how far off axis they meet? No. So I need to do one more thing. I need to send them through some additional distance S. You say, what is S? I don't know yet. All right, so I multiply all 4 of these matrices. These 3 are specified. This is unknown. We don't know what it is. So you're thinking, well, okay, we're just multiplying it by like whatever. No, it's not like whatever. We know one thing. We know that all of the rays that go at the same angle on the left side meet at the same y value on the right side, which means theta 2 y2 equals a, b, c, d, theta 1, y1. Just from knowing that they all have to meet at the same point on the right, what can we immediately say about one of the matrix elements?
That's 0.
Yep, which matrix element is 0?
Is D 0?
D is 0, yep, because y2 is c theta 1 plus d y1, and y and d is 0. So we use this condition to pick S. So 1, multiply our 4 matrices, including the translation. And I'm not going to write out all of the matrices. If I were to, we could do all the tedious algebra by hand, but there is a reason why Alan Turing invented the computer. And then we're going to solve for S so that D equals 0, because D is going to be some expression involving S. It might look really messy, but whatever it is, that's an algebra problem. Pick S so D equals 0. Well, now, how do we figure out the focal length? Y2 equals c theta 1 plus dy 1, but d was 0, so it's just c theta 1. Do we know anything else about the relationship between y2 and theta 1 that might tell us something about the focal length? It's
What
on
was
the
it that
what?
one said earlier about y equals f tan theta?
Yep. Every matrix optics problem involves at some point figuring out which matrix element is 0. If we want all of the rays to meet at the same point, regardless of what angle they started at, then that means that one of the matrix elements is 0. You're taking something from a finite distance over here to a finite distance over there. They all went in different directions, but they all meet up over here. So y2 depends on y1, but it doesn't depend on theta 1. The matrix element is 0. In other cases, we send in a bunch of rays, all at the same angle, all at different y values, and they all meet up here. And so we say that, well, y2 definitely depends on theta 1, but it doesn't depend on y1. So again, a matrix element is 0. That's all of matrix optics. Every problem we do, all right? If we were doing something like this case, something at a finite distance to an object at a finite distance to an image at a finite distance, y2 doesn't depend on, this was, y2 does depend on y1, it doesn't depend on theta 1. And then, well, up there, yeah, I don't know what we were doing. I don't know what case that was. So sorry, that was in this case here. Start over. Up here, y2 only depends on y1. Down here, y2 only depends on theta 1. Down here, y2 only depends on y1. Over here, y2 only depends on theta 1. For any matrix optics problem, that's what you're trying to do. You're trying to figure out, hey, a whole bunch of rays meet, which means that where they meet must not depend, can only depend on one of the variables, not the other. So let's go through that. I'm going to switch back to my other device. And we will skip some cases. We're going to do a lens that translates first through a curved surface, then it goes through some thickness, which I called T when I made this file. It's D in the diagram. Then it goes across another surface. Then it goes through this unknown distance X. So we do the multiplication and we get a mess. But we know that the lower right element of the matrix cannot possibly, that the lower right element of the matrix must be 0. So I had Mathematica write it out. This is just a fancy M double bracket 22 means lower right element. That's what we do. And we get this. And Mathematica hasn't yet put it in memory. Mathematica is saying, well, X would be this if you want to solve that equation. Then I have to go and I have to actually tell Mathematica to do that. So I say, okay, yeah. Mathematica is saying, hey, if you want to satisfy this equation, X is 0. But I haven't told it to set X equals 0. Because maybe I want to then see, well, what would X be if I solve some other equation? And then maybe I want to solve a third equation. I don't, but Mathematica doesn't know that. So Mathematica hasn't put this expression into the box in its memory that's labeled X. So I have to tell it to do that. And then once I do that, then I say, okay, well now X is equal to this. And the focal length is this thing down here, this lower left element, which is element 2, 1. So I tell it to simplify 1 over that element. And I told it to simplify 1 over that element, because if I tell it to simplify that element, let's just actually do that. I get, well, something messy. If I tell it to simplify 1 over that, it might still look messy, but it's not as bad. A whole lot of times in optics, formulas for 1 over F are easier than formulas for F. And I'm going to prove that. That'll be the last thing we do today. So for the thick lens, 1 over F, first thing I'm doing is just copying from Mathematica. It's equal to n minus 1 over n R1, R2 times minus the thickness plus n times minus R1 plus R2 plus the thickness. Okay, well, let's just take these things one at a time. That's going to be n minus 1. First, the thickness. I've got n times the thickness minus the thickness. All right. I feel like there's something wrong there. Okay, we'll just go with that for a little bit. Plus n minus 1 times n over n r1 r2 times minus r1. Let's see, that cancels there. The r1 up top cancels the thing down there. The n there cancels. And then I've got an n times r2. And r2, there's an n minus 1 out here. There's an n r1 r2. The n's cancel, the r2's cancel. And I'm left with 1 over f equals n minus 1 over r1. Ooh, this one has a minus sign in it, the second term. That's a minus. Plus n minus 1 over minus r2 plus n minus 1 whole thing squared times the thickness over n r1 r2. And
Doesn't
there's
it?
something I don't like. I feel like there's a missing minus sign somewhere.
Yeah, isn't the negative t instead of positive t up at the top when you distributed?
Yeah, except that it's NT. Are you talking about somewhere else? Like,
When you did on the second line where it's n minus 1 times n minus 1 times t, shouldn't that be times negative t?
let's see here. Minus t plus nt over n r1 r2. If I pull out a t, I've got negative 1 plus n. See, the thing is, I know that there's something wrong here. Because physically, if I make this lens really, really thick, then here's what should happen. And then we'll go, and maybe we'll pick up the troubleshooting next time. Apologize for keeping you late. If I make the lens really, really thick, then the parallel rays will come to a focus somewhere in there. All right, they'll come to a focus up there. Then they hit the second, then there's the second surface. And that second surface, well, you know, that ray will go like that. At that second surface, they'll come to a focus below the optic axis. So I know that the focal length has to be negative, because if I make the things really thick, then y is less than 0. So we've got a little bit of a mystery to solve here, but do you have any questions on the physical reasoning for why there must be something wrong? See, normally if the lens is thin, we know these first two terms are good. But if the lens is thick, then this last term will be huge. And it'll just dominate. We won't have to worry about the other two terms because this last term will be huge. And I know that if it's really, really thick, it should be negative. So I made an algebra mistake somewhere. I'm going to find my algebra mistake. Next time we'll pick up with my algebra mistake. Then we'll talk about how to interpret things with thick lenses, and we'll do some more matrix optics examples. And you have until Thursday to finish the assignment if you forgot to update the merit function for off-axis objects. Have a good evening.
Thank you, Dr. Small.
You're welcome.
Shouldn't there be a minus in front of the first term with the R1? Oh, or did you?
Let's go back into my other device onto Mathematica. Let's just look at it there. So I've got, this is n-1. This is minus t.
Oh, it's a minus t. So that, yeah, that flip positive. R2 is negative.
There's nt.
Wouldn't R2 be negative because of how you have the curvature set up?
Well, sure, it would be negative, but we've got negative R2 in the denominator. Oh, yes, I see now. Thank you. Yes. Okay. Yes, I see. Okay. Okay, thank you, Corey. Thank you. The error was not in my algebra. It was in my interpretation of the geometry. Got it. Thank you.
Yeah. Thank you, actually.
All right. Anything else? If people have questions, I'll stick around. Otherwise, if you gotta go, take off. Joshua, do you have a question for me? All right, I'm logging out.